So for problem 116, we are given the strain energy function nonlinear hyperelastic, which is this. And then in the first part, we want to find the stress tensor, which is the definition of the stress tensor as the derivative of the strain energy with respect to the E. And then now we use S equal to derivative of the strain energy with respect to EMN. We cannot use EIJ because we already have I, J, and K in the given equations. So here in the first part, we use the partial derivative, which is with respect to EMN, so II, and then MN, same thing to IJJ, and then IMN, and then same thing to IKK, IMN. And then for the second part, this one, same thing, IIJ, MN, and then you can see here. And then after that, we know that this term is equal to delta IM, delta IN, IN, same thing to all of the other function, delta JM, JN, the other thing. And then delta IM and delta IN, it goes to delta MN. And it's equal to 3 times delta MN AII AJJ, because here EJJ and EKK or EII is all the same, so you can just add, you can just sum it. And then for the second part is IM, IJN, and then here J and J, we can goes to E and K, same thing I, and then I, E, K, M, and then here, same thing, J, J, E, I, M, and then K, K becomes E and I, and then here too, K, K, E, J, M, I, J, and then I here, so you substitute E and J, and then here, since M is the row, and then N is the column, M goes here, M, and then M, and then for the rows, columns is in the beginning too. So everything here is the same, so we can sum all of them into A1, 3, E and K, E, K, M. So the final answer for stress tensor, we just sum the first term and the second term, which is this. Okay.
The next part of the problem asks us to determine if the material is isotropic or not. If the material is isotropic, it'll be a function of the invariance of the strain tensor. So our strain energy function here can be rewritten here. So the EII, EJJ, EKK can be written as the trace of E cubed, and EIJ, EJK, EKI can be rewritten as the trace of our strain tensor cubed. So if our strain energy function is a function of our invariance of the strain tensor, then we know that our material is isotropic. The next part of the problem asks us to find if the material is linear or not. We know that it's not linear because the strain tensor is a function of the stress tensor rather, is a function of the strain tensor multiplied by itself. So if the stress tensor function had only one strain tensor, but we have two, so we know that it will be a polynomial instead of a linear equation. So it's a non-linear material. And then the following section of the problem asks us to, well, it gives us this uniform state of shearing given by this strain tensor, and it asks us to find the principal values of the stress tensor S. So if we take our strain tensor and plug it back into our stress tensor formula, we'll end up with this. S of Mn is the first part will be 0 because we know the trace of the strain tensor will be the product of these 3 zeros. So that'll equal 0, and then the rest is A1 times 3 times ENK times EKM. If you noticed over here, we have Mn and Mn, so we'll need to reverse these two indices, but that's no problem because our strain tensor is symmetric, so we can just switch them since E, Mn will be, well, since the transpose of E is the same. So our stress tensor formula will be simplified to this, and the strain tensor times the strain tensor will be equal to that tensor there, and our principal values are our eigenvalues. So mu1 will equal mu2, and that's gamma squared, and mu3 will equal 0.